Imagine standing beside a 500-ton hydro generator. The turbine is spinning, thousands of gallons of water crash through the runner every second. The entire powerhouse vibrates with energy, but the generator is producing absolutely nothing. No electricity, no voltage, because the generator is missing a one critical thing: its magnetic spark. And without that spark, even one of the most powerful machines on earth become useless. Today I will show you the hidden system that secretly brings a hydrogen generator to life: the static excitation system. And the craziest part, before this system can even work, it has to solve a problem engineers call the chicken and egg dilemma. So inside a hydroelectric generator, electricity is not just created because the shaft rotates, and the machine first needs a strong magnetic field inside the rotor. The rotor is the massive rotating section connected directly to the turbine shaft. Surrounding it is the stator, and the stationary outer section packed with huge copper windings. Think of the rotor like a giant spinning electromagnetic. As it rotates inside the stator, its magnetic field cuts across the winding and electricity is born. But here's the catch: that magnetic field does not exist naturally. It must be created using a DC current. So that's the job of the excitation system. But now another problem appears. How do you send electricity into a rotor spinning at full speed? So this is where the exciter rings and carbon brushes come in. Mounted on the shaft at the top are smooth metallic ring called slip rings, or the exciter rings. These rings rotate together with the rotor. Pressing against them are stationary carbon brushes. So the carbon brushes stay fixed while the ring spin continuously. This creates a moving electrical connection between the stationary excitation system and the rotating rotor. So DC current flows through the carbon brushes into the exciter ring and finally into the rotor winding itself. That current transforms the rotor into a giant electromagnet. And once that magnetic field starts rotating inside the stator, the generator finally comes alive. Without excitation, there is no magnetic field. Without a magnetic field, there is no power generation. And surprisingly, some of the most critical electrical connections inside the powerhouse are literally sliding contacts rubbing against a spinning ring every second. So inside a large generator, dozens of carbon brushes may operate simultaneously. So these carbon brushes wear over the time, so the generator has carbon dust collectors. Like here, you can see there are two carbon dust collectors installed in this unit. The static excitation system has four major components. First comes the excitation transformer. A hydro generator may produce 15 to 20,000 volts AC, far too high for the excitation equipment. So the transformer steps that voltage down to around 600 to 900 volts AC. That power then enters the heart of the system, the Thyristor bridge. This is where the AC power becomes controlled DC current for the rotor. Inside the cabinets are electronic switches called thyristors. They open and close thousands of times every second like ultra-fast electrical gates. The AVR control exactly when those gates fire. Fire earlier, more DC current flows into the rotor. Fire later, less current flows, and that instantly changes the strength of the magnetic field. The DC current then travels through the brushes, through the rotating exciter ring, and into the rotor winding itself. Controlling everything is the AVR, the Automatic Voltage Regulator, the brain of the entire system. The AVR constantly monitors generator voltage in real time. If voltage drops, it boosts rotor current. If voltage rises too high, it reduces excitation. All of this happens automatically within fractions of a second. And finally comes the protection system, the field breaker and de-excitation circuit. Because the rotor is basically a giant electromagnetic magnet storing enormous energy, if the generator trips during an emergency, that magnetic energy must be removed safely. The field breaker disconnects excitation instantly, while discharging resistors safely collapse the magnetic field within milliseconds. Now, here is the engineering dilemma. The system normally gets its power from the generator itself. But during startup, the generator isn't producing electricity yet. So, how do you power the excitation system before the generator can generate power? This is where one of the smartest setup sequence in power engineering begins. It's called field flashing. As the turbine accelerates to near rated speed, the control system temporarily connects the station battery bank directly to the rotor, usually around 110 or 220 volt DC. That current passes through the carbon brushes into the exciter ring and energizes the rotor for the very first time. Suddenly, the stator began producing a small AC voltage. At first, only a few percent of rated voltage, but it is enough. Now the excitation transformer has power. The thyristor system wakes up. The AVR becomes active, and the generator begins exciting itself. At that exact moment, the machine becomes electrically alive. But even now, the generator still cannot connect to the grid because the electrical grid is brutally strict. Before synchronization, three things must match perfectly: voltage, frequency, and phase angle. The turbine governor adjusts speed to match grid frequency. The AVR adjusts excitation to match voltage.
सर ये ब्रेकर देखे अभी ओपन है ना हाँ वो एक वजह ब्रेकर लग गए
And when both waveforms align perfectly, the generator circuit breaker closes. That single click locks the machine into the national grid. Once synchronized, excitation no longer controls megawatt. Water flow controls megawatt. Excitation controls reactive power, MVAr. Think of a grid like a joint water pipeline. Real power, megawatt, is the actual water flow. Reactive power, MVAr, is the pressure inside the pipe. The turbine controls the flow. The excitation system controls the pressure. If grid voltage collapses, if grid voltage starts collapsing, the AVR boosts rotor current. The generator pushes reactive power into the grid to stabilize voltage. This is called overexcitation. Too little excitation causes underexcitation. And if it becomes severe, the generator can even lose synchronism with the grid. Inside a hydro generator, everything happens at massive scales. Huge magnetic field, extreme temperature, gigantic rotating forces. A single mistake can destroy equipment worth millions. That is why the AVR continuously run advanced protection system in the background. The overexcitation limiter prevents rotor overheating. The underexcitation limiter prevents loss of synchronization. And the volts per hertz limiter protects the generator core during startup and shutdown. Because if voltage becomes too high while frequency is still low, the magnetic core can saturate, causing destructive overheating inside both the generator and the transformer. And finally, there is the power system stabilizer, or PSS. This system detects tiny oscillation across the transmission network, then injects corrective signal into the AVR to stabilize the entire grid. In some situations, this system can literally help prevent regional blackouts. So the next time you see a giant hydro generator spinning deep inside a powerhouse, remember this: the turbine may provide the force, but the excitation system is what gives the machine electrical life. It creates the magnetic field, feeds current into the spinning rotor through carbon brushes and exciter ring, control voltage, stabilize the grid, protects the generator, and silently reacts to disturbances every single second. Without it, modern power system simply would not work. And the crazy part is most people stand inside a powerhouse, never even realize this hidden system exists. If you want to see more real engineering from inside actual hydropower plant, subscribe to Hydrovision, because the deeper you go inside this machine, the more unbelievable they become.